Hello everyone, welcome back to Sport Lecture. Today we have to continue to analysis about the footing and how to determine the substrate reaction of soils. And now let's start. We will discuss about the axial force applied on the footing. So we've got the axial, and this area is the fully distributed at the base, and the case we have applied the load and with eccentricity or with the applied moment, so the bearing stress at the base is not fully contact with the footing. We have the compression, and this one is the uplift. So how you can perform analysis in the case and in the case, so we will discuss in the next slide. Okay, this one the applied load with eccentricity or with the applied moments, and your contact pressure is not fully distributed at the base, so we suggest use the uplift analysis in CSI sales version 2016. You can use this type of analysis and convert to nonlinear analysis. And for this one, we can use linear analysis or compression only when you apply only axial force. Okay, when you apply only axial force, and the bearing stress will fully distribute in the base of the footing. In the case is the rectangular, okay, or linear. You see the contact stress, and this one we have eccentricity. And this is the property of soil when you apply the pressure. You see here the pressure, and this one is the deformation. So we can determine the Ks, okay, initial tension. If you find this angle, so you can determine it's equal to delta sigma, delta small lambda. So this one is the stress, and this one is the deformation. And according to the e-balls, and they use the experiment by applied load and a steel plate, and we got an settlement. You can see here settlement in cohesion soils, and this one is steel plate. And generally you can use the formula Ka is equal to applied, okay, soil pressure divide settlement. So you can determine the thickness, okay, Ks or soil, thickness of soils. And in the formula the e-ball use in inch, okay, in inch. So we need to convert from inch to millimeter. So 1 inch is equal to 25.4 millimeter. In the case we round up, we round down to only 25 millimeter. In the parameter Ka is the modulus of substrate reaction. You see here, this the modulus of substrate reaction of soils. We can model it's like a spring, okay, like spring support at the footing with deformation. So it has relationship between the deformation and the soil thickness, okay. And Q is the soil pressure, and the assumption for the allowable settlement is 25 millimeter. This limit is nearly from the allowable to the ultimate, okay. The settlement is not considered the plate or considered the foundation settlement. It only considered for the soil settlement. So this allowable soil settlement is 25 millimeter. And according to the Joseph E. Bowles Foundation Analysis and Design 5th edition, You can open the book on page 501 to 505, talk about this topic, about how to determine modular or subscript reaction using the formula. Actually, the experiment, and they can put the formula in inch, and we convert in from into the millimeter. And you see here, it is the actual formula, the first formula proposed by the Ebol. Ka is square, so indicate EQ ultimate, okay, and settlement here is 25 millimeter. We can put from here the small lambda is equal to 1 in. 1 in is equal to 25.4, but we round it down to 25, so we multiply it, okay. QU and small lambda is 25 millimeter, and if you want to convert from millimeter to mass, so it is equal to 40, okay. 1 divide 25 millimeter, 1 divide 25 multiply 10 power minus 3 met, so it's equal to 40. We want to convert the unit to kilonewton per square meter, and so you can take the Ka is equal to 40 multiply QU is the ultimate stress is equal to safety factor multiplied with the allowable stress. So we replace the ultimate stress with the available stress. You can compute the value. Ka is equal to 40 multiplied with the safety factor of load, and multiply with the this is the safety factor or allowable soil bearing capacity, and you multiply with the QA is allowable soil bearing capacity. So you can determine the KS, the modular or subscript reaction, by using the formula. Is equal to 40 multiplied with safety factor multiplied with the allowable soil bearing, okay. The unit in kilonewton per square meter per square meter. And in case you limit the settlement below this value below 25, so you can revise the formula again. The value will be smaller than 40. In case you limit the smaller time below the value, you can try to create another new formula by using this relationship, okay. This relationship, and if you want to use unit in imperial unit, you can use it in foot square foot per foot, and so it's equal to 12, because 1 inch is equal to 1 divided to 12 foot, okay. So you convert this unit, you will go to 12 multiplied with the safety factor multiplied with the QA, the allowable soil bearing capacity. So S can be equal to 2 or 2.5 or 3 or 4 according to soil report. You can use according to your judgment, or by geotechnical engineering provide you that safety. It depends on the soil and depends on the soil property, okay. It depends on soil or normal soil, so the factor can be vary from 2 to 3, okay. You can check in the books at the page 501 to 505. Shows says Ebol's Foundation Analysis and Design 5th edition. And now we explain you about the local axis, and in this slide we will talk about the soil spring assigned for the foundation for the pie, for the ball pies. And in SAS tab and SAP 2000 for the CSI user, and you should know about the location or the element. In this case, we can focus about beam or about the column. Is use the same local axis. For the local axis, one is red. You see here I highlight the red text, and this one the light green, and this one is the light blue. In the tab SAS and SAP use the light green and light blue, but in the GAD creative event design it choose the dark. Okay, the local axis red. You see here, this one is local axis red, and local axis Y is dark green, and local axis Z is dark blue in this direction. And for the tab, and SAS or SAP, they not choose local axis small local axis X or small Y or small Z, but they use 1, 2, and 3. So you can check for local axis 1 along the member. Okay, it's along member. Is this one is the pi, so the along the pi is the local axis 1, and local axis 2 is 1, and local axis 3 is 1. Now let's check about schematic or the definition. You see here, this one is the structural pier or ball pies components, and upper structure pie cap. So we can classify it in 3 different for the soil spring. The first one we can classify it the skin friction spring. You see here, skin friction spring. We provide you different spring. You see here, this one is the skin friction. We can apply it the line spring along local axis 1. You can check about slide about the local axis of the member. In this one we apply along the local axis 1, and this spring we call it lateral spring. We also apply it the line spring along local axis 2 and 3. Okay, 2 and 3, and at the end we call it earth bearing spring. In the earth bearing spring we can use the same with the shallow foundation. You can check about the previous slide in the reference of the bore well. In this one we use for the earth bearing spring. Okay, earth bearing spring. Now let's come back, and this schematic is the same, and we want to focus about the formula. You see here I highlight different color, this color, to illustrate about the skin friction. So you can calculate skin friction by using the formula 40 multiplied with SS and multiplied with the allowable soil bearing capacity. So after you got this skin friction, you can use for the line spring or the skin friction by multiply with the P the parameter of the ball pie. Okay, in the case we use the round pie, so you can multiply with the parameter of round section. And this one, and for the lateral, okay, lateral soil spring, you can use KS multiply with D. D is the diameter of the ball pie, or sometimes the U is equal to KS multiply with B. It's the same. B and D is the diameter of the ball pie. And at the end is equal to the soil spring. This formula is soil spring, but we call it different, call it the soil thickness or soil spring at the end. So use soil spring multiply with the AP, the section, cross section of the ball pie. This one we multiply with the parameter of price, and for the lateral we multiply with the diameter of pi, and for the earth we multiply with the cross sectional of the ball pie. And for the finite element analysis, nowadays you can use software to analyze the structural element. So in the case you can modeling in a sense soil spring in film software like a test shape or critic design or other type of finite element like Stat Pro. Okay, you see here, this one is the B diameter of a pi, or we can use is equal to D diameter of ball pie is the same. And this one is the soil spring, and this one is the soil spring, and the delta L is equal to the node spacing. When you use a finite element software, you can define node spacing. You no need to divide column into multi segment. Okay, in the case you do not need to divide your ball pie to 10 or to 5 segment. So you can use node spacing in software. ATEP also can use node spacing, and for the creative design you also can use node spacing. And we show you about how to use that option. And now you have to understand first about the K is equal to Ks. Okay, Ks you can determine according to the ball formula, and B. Okay, in B for this K we want to focus about the lateral spring. Okay, multiply with B. Okay, or diameter of pi, and multiply with delta L. Delta L is not the length of pi, but length of node spacing. So how to know how to provide node spacing? You should to understand about node spacing should be less than diameter of ball pie, less than or is equal to diameter of ball pie. It's important. Indicate your ball pie diameter is 1 meter. So the node spacing you should determine it below 1 meter from one node to other node. Okay, it's important because 1 2 3 4 5 6 7 8 2 6 7 2 4 6 7 nodes. So spacing from one node to one node, delta must be less than 1 meter. In case your ball pie diameter is 1 meter. So we use the same concept apply to the film software for analysis this type of structure. Okay, in a tab you can select one column. After that you select on the change and select on the frame. After that you can select the I'm sorry, this one. Now let me change it. Okay, again. And in a tab you can select member. After you select one member or multiple member, you can select it, and you click on assign and click on frame and click on frame automate option. So you can define automate option of this column or the ball pie. You should input it less than the diameter of the ball pie. This is for the CSI user, CSI product. And for GAD critic event design also have option. You can check on the all property, and you can select on one member or multiple member. You select on it, and you check on the mesh. You see here the number. You can input the number of the mesh: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see here indicate we input 10. So you can input this parameter number of the mesh. Okay, each one from one node to one node. Now we assign 10. We count it 10. So one spacing. Okay, one spacing from one node to one node. You should define it lower than diameter of the mobile. Okay, thank you for your watching. Thank you. I hope you enjoy this video. I hope you enjoy this tutorial. If you have any question to ask me, you can comment below in the my YouTube channel. I will respond you as possible. Thank you for your watching. Thank you. And for GAD user, graphic event design user, you can check in the graphic event design page about how to calculate the KTZ. Okay, KTZ. This indicate we calculate it manually by you can check in the page. Okay, ES1, ES2, ESN, and this one is the AB. Okay, the width and length, and you can check in this menu. And for the automatic calculate the subscribe modulus, you can check in my tutorial about how to design the manhole. Also show you how to use the automatic calculate the soil pressure and modulus reaction of the soil. You can check in this tutorial. For GAD also in this tutorial. Okay, and this tutorial, and this tutorial also show you how to calculate automatic soil spring in GAD. You can check in this tutorial. Okay, in this tutorial so show you how to calculate the soil spring. You can check. Now let's open design manhole in GAD. I also show you how to calculate automatic soil pressure with the soil thickness. Okay. See here below. See here this one I explained you about how you can use automatic option in GAD. Okay. Input the layer so or the automatic gravel or the layer also for this model. Okay, you can check the layer. Thank you for your watching. Thank you.